There is no rush tonight. Whatever you are doing today, it is finished now, or it will still be there in the morning. For the next half hour, there is nothing to solve. There is only a question, and the question is very old. What would happen if you fell into a black hole? Not what would happen to a spacecraft, or to a star, or to a planet unlucky enough to wander too close. What would happen to you? How long would the fall take? What you would see on the way down? Whether there is a bottom at all? We are going to take that question apart slowly, the way you would take apart a puzzle you are not in a hurry to finish. Some of the answers are strange. Some of them are stranger than the questions. And one of them, the last one, is that nobody knows. Let's begin somewhere gentle. Let's begin with what a black hole actually is, because almost everything you have been told about them is a little bit wrong. A black hole is not a hole. That word does a lot of damage. A hole is an absence, a gap, something missing from a surface. A black hole is the opposite of missing. It is the most concentrated presence that the universe knows how to make. Take a star, a real one, larger than our sun, burning through its fuel over 10 million years. For all of its life, that star is holding an argument with itself. Gravity is pulling every part of it inward, trying to collapse it into a point. The fusion in its core is pushing outward, trying to blow it apart. For 10 million years, neither side wins. That balance is what a star is. And then the fuel runs out. The outward push stops. The inward pull does not. And gravity, which has been patient this entire time, finally gets what it wanted. The core falls inward. Not slowly. In something like a second, a region larger than the Earth collapses to a region smaller than a city. If the star was large enough, nothing in physics is strong enough to stop that collapse. Not the pressure of atoms, not the pressure of the particles inside atoms, nothing. The matter keeps falling inward, and it takes its gravity with it. And the gravity gets stronger as everything gets closer together, and that makes it fall faster, which makes the gravity stronger still. What is left behind is not a hole. It is an amount of mass in a space far too small to hold it, and a region around it where the pull has become so strong that not even light moves fast enough to leave. That boundary has a name. We call it the event horizon, and it is one of the strangest objects in all of physics, because it is not made of anything. It is not a surface. It is not a wall. There is nothing there to touch. It is simply the last place from which you could still turn around. Inside that boundary, every direction that exists points inward, not because something is pulling you, but because space itself is arranged so that forward, backward, left, and right all lead to the same place. Trying to escape a black hole from inside the horizon is not like trying to climb out of a well. It is like trying to travel to yesterday. That is what you would be falling into. Let's talk about the fall. Black holes come in sizes, and the size changes everything about your fall. The most common kind is what is left when a large star dies, around 10 times the mass of our sun, packed into a sphere a few tens of kilometers across. If one were placed where you are sitting, it would fit comfortably inside a small city. You might think that a small black hole is the safer one. It is not. It is by far the worst place to fall. Before we go further, sit with what that size actually means. 10 times the mass of our sun. Our sun, which holds 99.8% of everything in this solar system. 10 of those, and the whole thing is 30 kilometers across. You could drive around it in half an hour if there were anything to drive on, which there is not. A teaspoon of that material, if you could somehow scoop it out and hold it, would outweigh every mountain range on Earth. That is not a large object. That is an ordinary amount of mass folded into an extraordinarily small amount of space. And it is precisely the smallness that makes it so violent. Here is why, and it has nothing to do with how strong the gravity is. It has to do with how quickly it changes. Imagine falling feet first. Your feet are closer to the center than your head is by not very much, perhaps 1.5 meters. On Earth, that difference means nothing at all. Gravity at your feet and gravity at your head are so nearly identical that no instrument in your body could tell them apart. Near a small black hole, that 1.5 meters is enormous. The pull at your feet becomes measurably stronger than the pull at your head. Not slightly, overwhelmingly. Your feet begin falling faster than your head, and since your feet are attached to your head, something has to give. Physicists have a name for what happens next, and it is a strangely gentle name for what it describes. They call it spaghettification. You are stretched, not crushed, stretched along the direction you are falling, while at the same time being squeezed from the sides. Because every part of you is trying to fall toward the same central point, and there is less and less room to do it in. And here is the part that matters for our question tonight. With a small black hole, this happens long before you arrive. You would be pulled apart hundreds of kilometers above the event horizon. You would never reach the boundary. You would never cross it. The interesting part of the journey, the part everyone wonders about, would happen to your remains, not to you. And if we ignore that and imagine that somehow you survived the crossing, the answer to how long the rest would take is almost disappointing. For a black hole of 10 solar masses, the fall from the event horizon to the center takes less than 1,000th of a second, less than a blink, less than the time it takes a single nerve signal to travel from your hand to your brain. There would be no experience of it, nothing to notice, no time in which to notice. So if you want to know what falling into a black hole is like, you have to choose a bigger one, much bigger. 26,000 light-years from here, in the direction of the constellation Sagittarius, there is an object we have been watching for 30 years. For most of that time, we could not see it. We could only see what it was doing. Stars near the center of our galaxy move in a way that makes no sense unless something enormous and invisible is sitting there. So astronomers tracked those stars year after year, watching them swing around a point where nothing appeared to be. They are orbiting 4.3 million times the mass of our Sun. That number was not guessed, it was weighed. There is a star there called S2, and it does something remarkable. It goes all the way around the center of our galaxy in about 16 years. 16. Our Sun takes 230 million. S2 is close enough and moving fast enough that astronomers have now watched it complete more than a full orbit. They have followed one star around the entire loop, night after night, for decades. And once you can watch something orbit, you can weigh what it is orbiting. It is the same arithmetic that tells you the mass of the Sun from the length of our year. Deep, calm, and steady, with a measured but flowing pace. Point the telescope, be patient for 25 years, and the answer comes out. 4.3 million suns in a space where we can see nothing at all. And then, in 2022, we finally saw it. Not the black hole itself, which cannot be seen, but its shadow, a dark circle surrounded by a ring of light that had been bent around it on its way to us. Telescopes on 4 continents working together as though they were a single dish the width of the Earth. We call it Sagittarius A star. It is the black hole at the center of the galaxy you live in.
Right now, while you are lying there, you are orbiting it. Everything you have ever seen is orbiting it. It takes the Sun about 230 million years to complete one circuit, and it is very large. Its event horizon is about 12 million kilometers across. To put that in a shape you can hold, the distance from our Sun to the planet Mercury, you could place the orbit of Mercury inside this black hole and it would fit with room to spare. Now, the thing about being that large is that everything changes. Remember the problem with the small black hole, that the pull at your feet was so much stronger than the pull at your head that you were torn apart before arriving. That problem comes from a sharp change in gravity over a short distance. Sagittarius A star is not sharp. It is gentle, in the only way that a thing like this can be gentle. Its horizon is so vast and its curvature so spread out that the difference in pull between your feet and your head as you cross it is small, small enough that you would feel nothing. Let me say that more clearly, because it is the strangest fact in this entire story. You would cross the event horizon of Sagittarius A star without noticing. There would be no boundary to feel, no membrane to pass through, no alarm, no shudder, no moment of crossing. You would be falling, and the stars would be around you, and at some point, a point you could not identify then or ever, the last opportunity to turn back would pass behind you silently, and you would not know. You would still be able to see. The universe would still be there. Your watch would still be running at what would feel to you like a completely normal speed, and you would have hours. That is the answer to the question in the title, and it is worth sitting with. Inside a black hole this large, the fall from the horizon to the center takes hours of your own time, not milliseconds, hours, long enough to think.
Long enough to look around. Long enough to understand where you are and what is going to happen, which is either a mercy or the opposite, depending on the kind of person you are. Let's leave you falling for a moment and go back to someone watching from a safe distance, because their version of this story is completely different, and both versions are true. Gravity does something to time. Not metaphorically, measurably. We have confirmed this with clocks flown on aircraft and clocks placed on mountains. A clock deeper in a gravitational field runs slower than a clock further out. On Earth, the effect is so small that it takes an atomic clock to see it. Near a black hole, it is not small at all. To your distant friend watching you fall, your clock appears to be slowing down. At first only slightly, then noticeably, then dramatically. Every signal you send takes longer to escape than the one before it, and the gaps between them stretch and stretch. And your light changes color. The light leaving you has to climb out of an increasingly deep well, and climbing costs it energy, and light that loses energy shifts toward red. So you fade, first toward red, then toward the deep infrared, then toward wavelengths no eye and no camera will ever catch. You slow, you redden, you dim, and you never arrive. There is a detail in that fading which is worth pausing on because it is quietly one of the loveliest facts in physics. Light does not leave you continuously. It leaves in particles, photons. A finite number of them, one after another, each one taking a little longer than the last to climb out. Which means there is a last one. Somewhere in that endless-looking fade, there is a final photon, the last piece of light that will ever escape from you and reach the outside universe. It leaves, it climbs, it arrives, stretched almost beyond recognition. And after that, there is nothing more ever from where you went. Your friend does not see you disappear. They see you dim until the dimming becomes indistinguishable from darkness, and then they go on watching a patch of sky that has nothing in it. And there is one more thing they do not see, which people almost always get wrong. You might have heard that as you fall in, you would look back and watch the entire future of the universe play out in fast forward above you. Galaxies aging, stars burning out, everything hurrying to its end in the last moments before you cross. It is a beautiful image, and it is not what happens. That effect belongs to a different situation, to something hovering near the horizon, holding its position, fighting to stay put. Hovering there, yes, you would see the outside universe racing, but you are not hovering. You are falling, and falling fast, and falling toward the very light you would need to be catching up with. For someone falling freely across the horizon, the outside sky does not race. It gathers, and it brightens, and it crowds into a smaller circle behind you. But it does not fast forward. You do not get to watch the end of everything. You get an ordinary sky seen from an extraordinary place. That is what your friend sees, not a fall, not a crossing. From outside, you approach the horizon and you slow down as you approach it, and you become dimmer and redder and more spread out in time, and you never quite get there. In their version of the story, you are still falling. You will always be still falling, frozen at the edge, fading toward invisible, taking forever. And inside, in your version, you crossed that boundary hours ago and felt nothing. Neither of you is wrong. This is one of those places where the universe declines to have a single answer. There is no view from nowhere that settles it. There is only what you experience and what they experience, and no way for the two of you to compare notes ever again. So you are inside now. You have hours. What is the fall actually like? For a while, and this surprises most people, it is quiet. You are not falling down a tunnel. There is no wind, no walls, nothing rushing past. You are weightless as you were before, because falling freely always feels like weightlessness. The stars are still visible above you, though they are gathering together into a smaller and brighter circle as you descend, crowding toward the direction you came from. That circle is the whole outside universe, and it is closing. It is worth describing what that sky looks like because it is not the sky you know. Light does not travel in straight lines here. It travels along whatever paths the curvature allows, and near a black hole, those paths bend. So the stars behind you appear shifted from where they truly are. Some of them appear twice, once by the direct route and once by a path that curved around the other side. Constellations you have known your whole life pull apart and rearrange, and near the edges of your view, they smear into arcs.
Deep, calm, and steady, with a measured but flowing pace. There is even a place above the horizon where the bending is so precise that light travels in a circle. Astronomers call it the photon sphere. A beam of light entering it at exactly the right angle will orbit, going all the way around and arriving back where it started. If you could stand there and look sideways, you would see the back of your own head lit by light that had made the entire journey around and come home. You will not be standing anywhere. But that place is real, and you will pass through it on the way down. And then, slowly, the thing that killed you instantly at the small black hole begins to arrive here too. Gently at first. A faint sense of being pulled along, a stretch you might mistake for imagination. Then not imagination. The tidal forces grow as you descend, and near the very end they grow without limit. Whatever happens at the center, you do not survive the approach to it. The last part of the fall is the same in every black hole. It is only the length of the calm part beforehand that changes. And what is at the center? Here I have to tell you the truth, which is that we do not know. Our best theory of gravity, general relativity, which has passed every test we have ever devised, which predicted these objects a century before we saw one, says that the matter collapses to a point of infinite density, a singularity,
a place where the curvature of space becomes infinite and the equations stop producing numbers. But when a theory produces infinity, that is not usually a discovery. It is usually a sign that the theory has been taken past the edge of where it works. Every physicist alive will tell you the same thing. The singularity is not a prediction we believe. It is a warning light. What actually happens down there requires a theory that combines gravity with quantum mechanics, and we do not have one. Not for lack of trying. It has been the central unsolved problem of physics for the better part of a century. So the honest ending to this story is that the fall takes hours, and it is quiet, and the sky closes above you into a bright, shrinking circle. And then it takes minutes, and then it takes seconds. And what waits at the end of it is the one place in the universe where our knowledge simply stops. One last thing before you sleep, because it puts everything we have said in proportion. Sagittarius A star, with its 4.3 million suns and its horizon the width of Mercury's orbit, is not a large black hole.
It is an ordinary one. In the catalogue of the universe, it is unremarkable. 55 million light-years away, at the center of the galaxy Messier 87, there is one that holds 6.5 billion times the mass of our Sun. Its event horizon is roughly 18 billion kilometers across, about 4 times the radius of our entire solar system. You could place the Sun and every planet inside that horizon, and the outer planets would still be well within it. Inside something that large, the calm part of the fall lasts not hours, but days. Days of falling, weightless, with the sky slowly gathering into a bright circle overhead in a place from which no signal you send will ever reach anyone, in the quietest region that exists. We began by asking how long the fall would take, and the answer turned out to depend entirely on how large a thing you fall into. 1/1000th of a second in the small ones, hours in the one at the center of our galaxy, days in the largest. And in every case, from the outside, you never arrive at all. There is something almost kind about how this works out. The black holes that would kill you fastest are the ones that would never let you cross at all. You would be gone long before the boundary, and there would be no experience to have. And the ones you could cross safely, the enormous, quiet ones, are the ones that give you the longest and calmest fall. The universe does not arrange its cruelties for our benefit, but in this one case, the arithmetic came out gently. The place you could actually reach is also the place that lets you take your time getting there. And it is worth remembering that none of this is hypothetical in the way it sounds. These objects are not ideas. They are not thought experiments. There is one at the center of this galaxy, weighed by watching a star loop around it for 25 years, photographed by telescopes on 4 continents working as one. It is there tonight. It has been there since long before the Earth existed, and it will be there long after. You are, at this moment, in orbit around it. Everyone you have ever met is in orbit around it. And the entire time, it has been pulling on you, gently, from 26,000 light-years away. The light from that black hole at the center of our galaxy, the light bending around it right now, has been traveling for 26,000 years to reach the sky above you tonight. It left before anyone had planted a crop or written a word. It has been on its way this whole time, through all of it, and it arrived tonight, quietly, while you were getting ready to sleep. There is no rush. Sleep well.